Thanks everyone for attending this tinyML talk. Today I have a pleasure to have Edouard Yvinec here, a PhD student from Datakalab, who is going to talk about post-training compression. I'm really looking forward to this presentation because most of the time we talk about tiny devices with, very important constraints in terms of memory. And definitely, I think this presentation will help and will benefit people that want to target applications on very constrained devices. So looking forward to learn more about how to compress these the machine learning models. I would say let's start from the first slide. Let's see. Yes. And from the first slide where we want to thank all the tinyML strategic partners that are making this possible. And here I'm gonna name all of them: AZ, Analog Devices, Arduino, ARM, Compass Marketing, Elgin Pulse, Green Waves Technologies, Grovit Inc., IBM, Imaging Mob, Innaterra, Microsoft, Not AI, NXP, OctoML, Pauling Technology, Kixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microtronics, Synaptics, Synchant, and TDK. So thanks again to our tinyML strategic partners. Definitely, we need to thank them for making this presentation and also the other presentations possible. Before we start the talk, a bit of housekeeping. And the first thing I want to highlight is about our tinyML community, which is growing and growing. We have over 13,000 members who join our meetups. And so it's great to see also new meetup groups, around the world. So definitely, we need to keep it up, this momentum, and I'm definitely looking forward to see other meetup groups growing and boarding at the same time around the world. Don't forget to subscribe also to the LinkedIn webpage if you want to be always up to date to our tinyML talks and other activities. Of course, if you want to learn more about tinyML, the best place to learn is here in the subscribing to the tinyML YouTube channel. Because here you can have, apart from the updates and notification, but also you have the videos of all our tinyML talks that we have delivered so far. And this is an incredible place to learn very simple things about the tinyML, but also complex stuff that our experts have been delivered in this field. So, well, definitely we need to dedicate one slide to the tinyML Summit, which is approaching very fast, and it will be in California, in San Francisco, from the 27th of March to 29th. And this is a great event to basically be always up to date to what is happening in this field. But at the same time to have to do networking with the players and people that are contributing and innovating in this area. The registration is open. You can click on the link provided in this slide. And also the Call for Summit 2023 nomination awards. So if you have something that you want to be recognized, don't forget to register. But if tinyML Summit is approaching fast, well, also tinyML EMEA is approaching. So we have the call for presentations open. The deadline is for the abstract is tomorrow. So you still have roughly 24 hours to submit something for the event. I will be there, and it's honestly, I'm looking forward to join the tinyML community in Amsterdam this June. But our events do not stop just at the tinyML Summit and the tinyML EMEA, because tinyML is also at the Embedded World 2023. And here we'll be from 14th of March to the 16th of March in Nuremberg in Germany. So the tinyML will have a dedicated pavilion and exhibition, and there will also a technical session at the conference chaired by the professor Daniel Müller Gritschneider from TU Munich. So it's great to see tinyML everywhere around the world to spread the knowledge about this fascinating field. And I think that's it. So I'd like to introduce Edouard Yvinec. Is a PhD student at Datakalab at Sorbonne University. Neural networks compression is his main research interest, which he applies to solving computer vision and NLP tasks. He published several works on post-training compression, for example, at NeuroIPS, on quantization at IJK, on layer folding. Each of these methods focus on computer vision tasks solved by convenience, to the exception of PowerQuant, which also tackled transformer compression for both vision and NLP. So thanks again for joining this talk, and welcome Edouard Yvinec. Looking forward to learn from your presentation how to the techniques for the post-training quantization compression.
Well, thank you so much, Gianmarco, for the introduction. So as was said, we're going to talk about post-training compression, how we go from the lab to the edge. So just to put an example here, because I come from the computer vision community initially, what we would do, we would have our favorite framework to work with, TensorFlow, Torch, whatever. We train the neural network, and as I think most of you know, this process can take a lot of time. And once we've reached satisfactory accuracy for the task at hand, we usually like to not go through too much trouble to actually use the network at inference. So for this reason, most people tend to use the same machines that they use for training during inference. And that's why so many people make the mistake to keep using the cloud for inference. And well, I don't have to convince you at the tinyML community that this is a mistake. And we will see how here at Datakalab we have developed quite a few solutions to actually enable inference on edge devices. So how this works? Well, you keep on using your favorite framework, TensorFlow, PyTorch, and you send us your trained neural network. And what we do is, with a little bit of magic that we will detail in a few seconds, we give you back something that you can use for deployment on the edge for your favorite dedicated hardware. So essentially, you can insert back the slide with the sponsors here. So essentially, what we've managed is through engineering, having code that can compile models and give you something that can run on your favorite edge device. So let's go into slightly more details. So what we do at Datakalab is can be split in three subcategories. So if you're familiar with what's done at the tinyML presentations, you've heard about pruning, you've heard about quantization. So of course we do those. We have improved upon the state-of-the-art methods, but we also offer two other bricks. The first one will be context over compression. So this will be my last part of the presentation, and also model compilation. So this I will not detail, but essentially what it does, it outputs something that can run, actually efficiently run on the dedicated hardware. So let's start with something that we are most familiar with. So post-training quantization. So here we go from the work of Qualcomm. The idea is you receive some trained neural network. Usually it achieves satisfactory accuracy. You may share a calibration set that's standard in post-training quantization, but here at Datakalab, because we come from a place where GDPR is very, very important, what we do is we consider that the calibration set is empty. So in the literature, that's called data-free quantization. And what you do is you want to actually find a way to transform your operations from floating point operations to fixed point operations. And the huge advantages of post-training quantization over other techniques, first of all, it's production ready. So what that means is it uses operations that are already supported by the inference engine, by the hardware. It's GDPR compliant. So to put it in simple words, we don't have to worry about data privacy because we don't use any data. And it's fast and simple. In other words, it takes a few seconds and up to a minute to actually quantize the neural network. So, of course, I expect you to be familiar with this kind of slide. So on the left, we have what you get from the standard TensorFlow PyTorch kind of inference, so floating point with large bit width operations. And in quantization, we want to actually map the operations to low bit operations with fixed point representations. So here, the idea, the challenge is to preserve the predictive function in order to have the great accuracy, but benefit from lower bit representations, hence much faster, lightweight neural networks. So this is actually important not only for tinyML. This is like a little sidestep from the conference here, but this is also very important for GPU inference. As when you run on the cloud, obviously you don't pay per the operation, you pay per the second. So if you can do much more operations per second, that's beneficial. But obviously on the left, for all the very tiny devices, you have to fit the model in memory, and quantization is a very efficient way to do so. So now that we are all enthusiasts for quantization, what do we offer here at Datakalab? Essentially, it can be decomposed in 3 steps, 3 separate problems in data-free quantization. So the first one is about per-channel quantization. So here, what we will see is how we can manage to have per-channel quantization on both the weights and the activations without actually cheating the process and without having to change the kernels, without having to do some heavy lifting. The second part will be about non-uniform quantization, and the last part is my personal favorite. Essentially, it's about leveraging your hardware to the fullest. So, about per channel versus per tensor quantization. On the left, we have per channel quantization, and on the right, we have per tensor quantization. What you expect is, because you have in that case for a fully connected layer matrix multiplication, per channel quantization, because you group the sub-values of the tensor in a finer grain, what you get is something that is closer to the original values. To put it in simpler words, we are tighter to the original distribution that we want to quantize. The issue is that, as you can see, the inputs are not quantized per channel. The reason is highlighted in the equation below. So that's the only big equation we have. I don't want to be painful during that presentation. Essentially, what we get is, if we were to do per channel quantization on both the weights and the inputs, that would mean that for every single multiplication, for each and every individual multiplication, we would have a distinct scaling factor. So that's illustrated on the left. The issue is that for the hardware to efficiently leverage this per channel quantization, you want to have one scaling factor per scalar product. So that's the right-hand side of the equation. So to put it in simpler words, the idea here is that on the left is what you get when you want to have a very tight fit to the original distribution, and on the right is what's fully leveraged by the hardware. So what we did, and we published this work at WACV this year, is to find a way to actually have per channel quantization on both weights and inputs, but still remain on the right-hand side of the previous equation. And how we do that is fairly simple. What we want to do, the weights, the quantized weights, instead of simply approximating the full precision weights, they do 2 operations at once. First operation, the learned matrix multiplication. Second operation, the dequantization of the inputs. So if you're very familiar with the literature, this can be, you can make connections with cross-layer equalization. The difference is that cross-layer equalization was thought for per tensor quantization, and this is the equivalent for per channel quantization. So here, we illustrated on the right the impact on the feature maps, so at several levels of ResNet 50. And we compare for a standard static per tensor quantization to dynamic quantization and to per channel, the proposed per channel quantization. And what we can see is that we preserve the representations much better. So obviously we achieve a higher accuracy. And I want to put the emphasis on the fact that some networks are very challenging to quantize, especially efficient nets, for instance, or mobile net v3. The reason behind that, one of the reasons, would be the SILU. The SILU has a negative slope that is very small. And because of that, if you have one per tensor scaling factor, if you have discrepancies between channels, which is the case in practice, for smaller value channels, what you would get is that the very tiny negative values will be rounded to 0. So essentially, you have forcefully converted a SILU to a ReLU. But that does not happen if you have per channel quantization. So that's why Spike works pretty well on efficient net-like architectures. Now, that being said, it's far from enough to achieve very good accuracy with 4 bits. This is very challenging with data-free quantization. And to actually do it, we propose to focus on non-uniform quantization to have an even better fit to the distribution we want to quantize. So just a brief reminder of what is non-uniform quantization. So on the left, you have quantization as we know it. We map floating point values to integers using, using rounding. And on the right-hand side, you have the standard non-uniform quantization, which actually maps multiplications to bit shifts. And that's what I mean when I say custom implementation. So on the left-hand side, what we get is something that is not very tight to the distribution, but is easier to leverage because it's already supported by most hardware. On the right-hand side, it could be supported, but in practice, it's not so often the case. So what we wanted to do in that paper called PowerQuant that was published this year at iClear was to find non-uniform quantization transformations that map a multiplication to a multiplication. So such transformations are essentially automorphisms, and that's just, in that case, a fancy word to say power functions. So here with PowerQuant, what we want to find is the best suited power function to fit our initial distribution. And what we found out is that in most instances, the best transformation is the square function. So obviously, the square function is well supported by most hardware. It can be implemented using only integer values. And what we observe is incredible results across a wide variety of networks and applications. But I want to put the emphasis on transformers. I mean, transformers have become a huge trend. I mean, unless you don't have any internet access, you've heard about GPT and so on. I mean, even before DALI and all that stuff, it's all about transformers, and they are very challenging to quantize. But what we can achieve with PowerQuant is using half the bit width, we outperform other data-free quantization schemes. So we can bring almost the full precision accuracy without using more than 4 bits for the weights to quantize. And I mean, obviously, it works very well also on efficient nets, mobile nets, comp nets, as you would expect. And we also tested it on NLP, and same results. PowerQuant gives huge benefits over other data-free quantization schemes. But now that we've seen how data-free quantization can lead to huge compression and how we can improve upon existing methods, I want to ask you one simple question. In practice, most of you know that your hardware will not support any bit width. Like in that example, when we have one GPU from NVIDIA, I mean, I know it's kind of an offense at tinyML to put a GPU as an example, but you can replace that with your favorite tiny edge device. It would be essentially the same. It will most likely well support a limited number of bit widths. And if your quantization scheme only works with at least 5 bits, or let's say 4 bits for the weights and 8 bits for the activations, you're probably stuck using 8 bits for inference, or you will have something that does not actually, it's not actually well leveraged by your hardware. So here the idea is to figure out a way to use your quantization scheme while remaining on the good bit width for your hardware. And how we do that is simply by using residual expansions. So residual expansion, the intuition is fairly simple. Quantization introduces an error, simply the difference between the original distribution and the quantized one. And that error can be also quantized. So now, instead of having, let's say, one matrix multiplication, you have two matrix multiplications. The first one being the standard quantization result, and the second one is the residue that has also been quantized. So now what you can do, let's say that you required 5 bits to have the full precision accuracy. You can use 4 bits for the first residue and 1 bit for the second residue. So what you would get is 5 bits that are actually well leveraged by your hardware, but only using the quantized operation and the residual method. So here is an illustration of that. Essentially, if you can see the little pentagons, they are what you would get from the naive quantization approach using your favorite quantization operator. And as you can see in that particular example, you're stuck using 6, 7, 8 bits. So in practice, you're stuck using 8 bits. But using Rex, what you would get is, because you have all those trade-offs using different bit widths, you can actually use something that requires less bits operations across the network to run one inference and still have full precision accuracy. So with that being said, what we've uncovered with this part of the presentation is that here at Datakalab, we have state-of-the-art quantization operators, and we also have a way to fully leverage your hardware regardless of the bit width that are supported or not. Now, let's say that you have quantized your network. You want to go one step further. You want to compress it even further. The standard second approach would be pruning. So at Datakalab, we had previous work on quantization, on pruning, sorry. I won't go into the details for those ones. If you're interested, they were published at NeurIPS and TPAMI. I just paused the QR codes here if you want to check them. Essentially, the idea is to remove redundant operations. Those are data-free pruning. So they can give a slight improvement in terms of inference, but they're not as impressive as the next pruning method that I'm about to present. So this method was also published at NeurIPS, and this is an opportunity for me to talk to you about the tinyML perf competition. So if you're not familiar with this one, so there are several tracks. We focused on the one with the ResNet 8. So here you have a ResNet 8 that is trained on Cypher 10. And what you want to do is compress it and remain above the 85% accuracy threshold. And what we've done with this method, which is essentially inspired from attribution. So if you're familiar with attribution, it's a subfield of explainability. The idea is to find out which parts of the inputs are the most important. And to do so, we have a baseline, which usually is a black image, and we have the input that we want to study. We sample a linear grid between the black image and the original input. We compute some standard attribution metric, such as the gradients, for instance, and we just compute the average over all the data points, and that's what is the integrated gradients. In our case, we adapted the method to actually extract the most important weights. So instead of extracting the most important inputs, we extract the most important weights. In our case, going from the original weights to black weights, which would be the pruned weights, actually makes sense. And that allows us to figure out which weights are more important. This can be done in structured and in unstructured pruning. So that's why we have the results here with NXP. We also run the tests with ST hardware. So essentially, using structured pruning, we can remove about 2/3 of the network. So that's quite huge, especially as compared to other techniques that struggle to remove above 45% of the parameters. Here we achieved 66%. And with unstructured pruning, we actually tested it using Neural Magic inference engine, and we can remove about 80% of the parameters, which again is huge, and we can double the throughput on the tested hardware. So that being said, we've seen that at Datakalab, we can do very efficient quantization, very effective pruning. All those are already known. We actually improve upon what's existing. But here, it's, to me, let's say, the most interesting part of the presentation, because it's something that is, for most of you, quite new, I suppose. Context-aware compression. So to illustrate this, I hope the video will run. So what you should see, on the left, you have your YOLO v4. This will not run on your tiniest edge devices, way too big. That's why it flickers, that's why it lags a lot. So what the beginner in tinyML would do, well, I will try to build some similar architecture. So that's the video in the middle. I will train it on my favorite data set, probably Coco, and this is what I will get. Because the model is so small, what you've seen on the video in the middle is something that is way inaccurate. That's something that you cannot be satisfied with. And if you've seen, maybe I can restart the video. Okay, so on the right-hand side, we have what we can achieve with Datakalab. So essentially, we have something that is similar in size as what you would get in the middle, but we have something that is similar to the left side in terms of accuracy. So the question will be, how can we achieve that? Okay, so just for the sake of clarity, here is what you would get if you were to pipeline the first solution. So your network is way too big to be run continuously on your small device. So what you would do is the local device uploads the data to the cloud, the network infers on the cloud and sends back the prediction. So obviously, I don't have to convince you that that's not satisfactory. You are not GDPR compliant. This requires high cost, frequent access to internet. I mean, but again, it's fairly simple to pipeline to nowadays. Now, the beginner solution to tinyML in tinyML would be, I train, as I said, my small network on Coco. I test it straight away, and I will have a low accuracy just simply because my network is so small. So that's the setup. We have a trained network. So as a client, what you would give us, you have your trained network, you give it to us. Eventually, you have designed your own student, or maybe we design it for you. That's up to the individual case. And what we want to do is have the accuracy of the big model on the small model. So that already should ring some bells about distillation and stuff like that, but we'll see about those details. So how can we do that? Essentially, what we'll do is specification. Instead of being able to work on every single example of your training set, where you have people on skis in the mountain, you have people on the streets, you have people in their toilets. I mean, you don't want to be precise in all those contexts. You want to be precise in one target context. So going back to our small pipelines, this is what you would get. So the continuous arrows represent continuous inference. Your small model is built to work for continuous inference on your dedicated hardware. What you will do is you will use the teacher, the large model, to extract a ground truth and use it to retrain your small model. And if you're familiar with distillation, you might catch the fact that this blue arrow actually hides a lot. I mean, the big question would be, okay, but how do I select which example to train on? How do I make sure that, okay, I become specific to the context, but I don't become too specific to the few examples I've seen? This is very challenging, and we at Datakalab add some layers of continual learning to avoid catastrophic forgetting. We add some layers of dataset pruning to select the good examples to train with. And there is a lot of engineering behind that blue arrow. And I will not have the time to go into the details, but if you have any question about this, feel free to ask them and to contact us about this. But there is one last question I need to address before going to your question. Because I kind of cheated here. I said I cannot run my large model on the local device, and I just said I used a large model to extract some ground truth, which means that I can run my large model once in a while on the edge device. What if my model is so big, let's say it's GPT-like in size, and there is no chance that I can run it on my tiny hardware? Well, what we've studied here at Datakalab, taking inspiration from deep inversion methods and stuff like that, where can you cut your network to extract intermediate features in order to send them to the cloud, and then infer the last parts of the model, and then send back the ground truth. So here, what we've done, thanks to that, so it's very challenging and depends on the architecture, because you cannot cut anywhere as you'd like. That takes quite some sophisticated techniques, but the idea here is fairly simple. You infer the first parts of your model, and the first part of the model extracts features, but those features by nature do not contain the identity, or I should say, you cannot retrieve the identity of the people, or let's say the cars, or let's say the voice, or whatever, from that intermediate feature. So that intermediate feature can be in a GDPR compliant way sent up to the cloud. You can infer the last layers on the model, extract the ground truth, and then again that blue arrow with this all this continual dataset pruning, stuff like that. So that being said, we've tested this. So for the benchmark, obviously we have to take a few steps from the usual benchmark, let's say for object detection, because what we want to do is to actually train on a very specific context. So here, how should you read those graphics? Essentially, we want to go from the lower horizontal bar of the baseline student up to the teacher. We want to match the accuracy of the teacher. And what we've done is, on the axis, is how many frames you select for training. And we test in a subsequent sequence of time. And what you see is that, well, you should see two things. First, well, we converge to the accuracy of the teacher, so that's good for us. But the second thing, which is the most important, is it's very chaotic. You have a lot of variance, and that's where this continual learning, this dataset pruning comes into play. It's how can you make sure that you are at the top of the training curve and not at the bottom. And lastly, with this confusion matrix, what you would get is the demonstration of the specification. So essentially, you have 6 contexts, and we perform a cross-validation, or I should say cross-evaluation. And what you can see is in the specific context, so in the diagonal, you have huge accuracy. I mean, you actually match the accuracy of the teacher. And when you test the model on a different context, it does not work. But that's actually something you want. I mean, if you have, here I gave examples of object detection, but let's say I want to apply the same technique for voice recognition. Let's say you have your home pod. I don't want the model to be trained at your place for your personal usage to work very well at my home. I mean, that does not make sense. So that's the whole idea. You want to be very specific to a context, and that's what we achieved. And obviously, it's the improvement over the baseline is significant. I mean, if you're familiar with object detection, 30 points in MAP, it's huge. I mean, it's not comparable. So to wrap this up, I mean, I think there was quite a lot to cover here. Essentially 3 building blocks. Each can be used individually. If you want only one of those, that's fine. If you want all of them, that's better. Pruning, quantization, standard methods, we improve upon above the state of the art. Quantization, aware compression, quite new technique, not a lot of work in the literature about this. We're quite proud of it. And finally, model conversion, compilation, all about mapping your network your train network to the to your favorite hardware. And well, thank you a lot. I see that we have a few questions. I'll gladly answer them. Please visit us at the website, and one other reminder of the tinyML Summit. Come see us there in exactly 1 month, and you can register using the QR code. Thank you so much.
So thanks a lot, Edouard, for this brilliant presentation with quite a lot of technical details presented, and I'm pretty sure we're going to have a lot of questions. So, okay, I think we can start from the questions I can see here on Zoom. I also have some questions on my side. The first one is about pruning. For structured and unstructured pruning, how is the results compare for a single hardware?
Okay, so it's we don't have the comparison for the same hardware. The reason being that we tested it from for the structured pruning was tested for NXP and ST using their inference engine, while the unstructured pruning results come from the Neural Magic, so tested on Intel CPU. So I know that Neural Magic released recently a version of their inference engine for ARM devices. So we could test on the same device, but from what we've gathered, essentially, the results are more related to the size of the hardware. Let's say if you have a very, very small hardware, what you would get is less impressive results, just because you're already so close to the uncompressible runtime. While for the unstructured pruning and on the larger devices, using the inference engine and the sparsity gives huge benefits. But we don't have the comparison on the same hardware.
Okay, so there is a follow-up question on this. Can you tell how they compare each other in terms of parameter reduction? Also, can you suggest the papers where it has been discussed? Yeah. Is it something? Yep, go ahead.
Yeah, so to compare structured and unstructured pruning, well, of course, I will sell my own work. You can check the paper I presented, so I can go back. So you have the okay, so you can have the QR code. Essentially, we've compared the results between structured and unstructured. What you would expect usually with structured pruning is to remove about 50–60% of the parameters using the best techniques. With unstructured pruning, you can go up to 90–95% of the parameters. And usually they result in similar inference benefits. In the paper, we make the comparison, and we also refer to other papers that also do this comparison.
Okay. Thanks for the answers, Edouard. So there is a question actually quite similar to the one I wanted to ask. Have you open sourced the code associated with the papers presented here today?
Okay, yeah, so that's a very good question. So that would be a better question to ask my CTO. But what I can say about that is we have open sourced some papers. So one paper was published at ISHCAI on batch normalization folding, where we have an optimal method that actually solves the graph and stuff like that. So this is open source for TensorFlow models. We plan on open sourcing Rex, Spike. So those are a work in progress. We're making them compatible for Onyx models. So as you may know, if you work with PyTorch or TensorFlow, you can go to Onyx quite simply. And for the rest, I think the best way to have the complete answer is to register for the tinyML Summit and ask the question there to my colleagues.
Okay, many thanks. Another quick one, which is related to one of your first slides. You said at the beginning you have trained your model in TensorFlow, PyTorch, or any other frameworks, and you give this model to us, and we provide the optimized model for the platform. How do they give this model to you? I mean, is there a framework? How does it happen, this process, in a few words?
Yeah. So as of today, there are several solutions for that. Essentially, they send it. So as of today, we are making proof of concepts. So they just send it. I will say, to put it an example, a simple example, by mail. You just send the saved model, binary model, and you just send your model in any way. We plan to have a platform for that. So essentially, you just upload your model, and we return the compiled version and compress.
Perfect. Thanks. Another question on Zoom. So for using the large model as a ground truth supervisor, is it a procedure that is supposed to be always on and improves the small network over time? Or can this also be done in a few short learning setup before distribution of the product?
Yeah, so that's a very good question. So actually, it can be performed in any way you want. So let's say, I'll give two examples. Let's say you know that your context is the subway, for instance, and you will not have a lot of variations across the day and from a day to another day. So in that case, the process will be done once. You will have the few shot learning, as you mentioned. So that, yeah, so that's one of the keywords here if you want to look up the literature. And then you just use the train model and you discard the teacher, and then the process is done. Now let's imagine that you have something that depends on the weather, or maybe something that can change from one month to the other. Let's say you're on the street and maybe there is some work that is happening outside, and maybe you have to, at some point, refine tune the model. So the process, usually how we do it, we perform the fine tuning for a few steps, and then it goes down to sleep, and you infer with your trained student for quite some time. So yeah, essentially, it's very related to few shot learning. Yeah.
Okay.
Just sometimes you wake it up.
Thank you. Another question on Zoom. For continual learning, the labeling will be done in the cloud?
Yeah, okay. So about continual learning, so that can be done again. So we have two scenarios, essentially, if I go back. So we have the scenario where the labeling is done by the teacher. So that's done on the local device. And the scenario where the teacher does not fit on the local device, and you have at some point to infer part of the model on the cloud. But all the continual learning is about the training procedure. And the training procedure is performed on the local device. So that's I think that's very important to keep that in mind, because if you want to do the training procedure on the cloud, you have to keep all the intermediate activations on the cloud. And because of that, you will not be GDPR compliant, because you will have the activations of the first layers, and those first layers contain the identity informations, and therefore you can retrieve from the activations the identity of the people on the data stream. So yeah, in the distillation, the continual learning stuff is happening on the local device.
Okay, and still related to the distillation, can you explain again why the distillation scenario is GDPR compliant?
Yeah. Okay. So to be GDPR, what you have is to satisfy a few constraints. Essentially, you don't send the data to the cloud, and you don't store the data on the device. That's the main aspects of GDPR. There are other stuff, but that's the most important side. And here, why are we GDPR compliant is because we obviously don't send the identity to the cloud. So that's the aspect I focused on. And the other aspect is that because we perform the training immediately, we don't have to store the input. So essentially on this little pipeline, once you have done the inference with the student and the teacher, or just the student if the teacher is silent, you just discard the input data. So you don't store anything on device. And because of that, you are GDPR compliant.
Okay. Thank you. So there is a question here, but actually probably is more for me, this question. Are you going to post this talk somewhere? Yes, we are going to to make this the recording available, I think maybe already from tomorrow on YouTube. So you just need to subscribe to the YouTube tinyML channel. You will receive the updates on when these new video will be available. There is another question. So does it make sense to try to apply these techniques in the context of running convolutional networks on FPGA? Potentially more flexibility of number representation. I believe here we are talking about the bit width.
Yeah. So yeah, if you want to run on the FPGA, I would strongly advise to use PowerQuant. Because the most challenging part of PowerQuant is that power function implementation. And as far as I know on FPGAs, this can be very efficiently implemented using lookup tables. So yeah, I mean, obviously Rex would be less of, let's say, a method of interest in the case of FPGAs, but then PowerQuant becomes way more interesting. So yeah, some of those methods are very interesting on FPGAs, especially if you have, let's say, a design that is oriented on memory access. You want to be very efficient at memory access and, let's say, less efficient using computations for some reason. Then we have some pruning techniques that would leverage that very efficiently. So yeah, for FPGAs, some of our methods are very efficient, yeah.
Okay, thank you. So we have also answered this. So on Zoom, we don't have any more questions. Probably, okay, there is a one. So how does residual quantization perform while you have lower precision input weights? It seems like you are increasing the number of computation n times. What is the good number of residuals?
Yeah, so thank you for the question. You're correct. We have increased the number of operations, but we're using usually lower bit width representation. So it's about finding better trade-offs, not using the bit width, but using a fixed bit width that is well supported by the hardware and using instead the expansion. I didn't focus on this in the presentation, but we have a sparse version of the expansion. So where you use a fraction of the residue. So just to give some numbers, let's say your hardware supports ternary quantization. Usually 3 or 4 residues is enough to actually reach the full precision of the model. Using 4-bit representation, you can use only 25% added operations and still recover the full precision accuracy. So let's say you use your favorite post-training quantization technique. Let's say you could use break, Q-drop, add around, whatever, where usually you lose 3 to 4 points of accuracy using 4 bits. What you would get using 4 bits plus 1 ternary quantization, you recover the full precision accuracy. So that's the main idea.
Okay. Thanks. So the other few questions. So one is about the paper so about the idea of the large model ground through supervision. Is there a paper for that?
So in one word, no. In 2 words, not yet.
Okay. So it's gonna be soon.
Hopefully.
Okay. Good. Thanks for the question. Thanks for the answer. So do we need to pre-process the data in a particular way to be ready for tinyML application? I think this is general. If you wanna answer this question, otherwise I can answer.
I'll let you answer it.
Okay, so the correct answer for all the questions is it depends. So it depends on your application. So in particular cases, the pre-processing is needed. For example, for acoustic models, for audio, the pre-processing is most of the time required because feeding the machine learning model with raw data does not perform really well in terms of accuracy. And that is the reason we need pre-processing. Just to give an example, the extraction of the MFCC coefficients is one of these. For vision applications, it depends. Maybe the preprocessing is a bit lightweight because you can feed the model with raw data, which are your pixels, but sometimes you need to apply the preprocessing to remove the noise, or to apply a bit of filtering, or to crop a specific area of your model. So it depends on your applications. Hopefully I answer your question. So I have one question for you about the context-aware quantization. I really like the idea. I really like the idea. And I believe the idea comes from the fact that you can, you don't have data from the people that is gonna give you the model, right? So the context-aware comes from the fact that, okay, I don't have the data to retrain my model. Where can I get this data from the field? Is it correct?
Yeah, that's one part. Yeah, that's one step. Yeah, definitely.
Okay. That's perfect. Okay, any other questions? There is one more. How are the sparse computations handled in neural networks? I mean, let's say if there are lots of zeros in the image or data, you don't have any information, then how would you avoid those computations while using convolutions?
Yeah, so here I will have to do some advertising for not the competition, but some other people working on tinyML. Essentially, what you require is an inference engine that actually leverages sparse matrix multiplication. And in the community, they're not the only one to do it, but this is the first example that comes to mind. Usually it's Neural Magic. So if you want to look them up, they can actually leverage sparse matrix multiplication, yes. But it's not straightforward, and it's not native on most inference engine.
Yeah, and the other thing probably that we can mention, I mean, this information is evaluated on the weights, something which is constant, of course. This evaluation cannot be done all the time for the inputs or the activations. So this usually happens offline. So from the weights, you know where the zeros are, and in somehow you can skip the computation for those zeros. Any other questions? Quite a lot of questions, I would say. So definitely it was super interesting. I learned a lot today.
Well, thank you. Okay,
let's wait just 30 seconds so to see if we have any other questions. If not, I proceed with the last slides of this talk. Is it better to start from a small network or a larger network to shrink it to a smaller size?
Okay, so that's quite a broad question, actually. What I would say is depends on the task and depends on the accuracy you want to reach. Essentially, I would say it's the best you can do is to start your compression journey with a model that is as small as possible, but has an accuracy that you find satisfactory. So that's essentially what I wanted to highlight when I talked about context-aware compression. The naive approach to have a small model run on your edge device is to actually design a small model, train it on the large data set, and see if it can perform well. But when you want to target extreme scenarios where, let's say, you want your model to have less than 100K parameters, and you want to tackle very challenging tasks such as object detection in the wild, you will most likely not be able to perform the general case. So it's about choosing your battles, and it's about starting already as small as possible, and then apply quantization pruning to just remove the extra non-necessary computations. But I would say try to start as small as possible, but again, above your accuracy threshold.
Thanks a lot for this answer, for the question. Okay, I think we have finished with the questions, so I can probably proceed with the following slides. So again, I'd like to thank all the tinyML strategic partners for making this presentation possible, but also the other tinyML activities. So thanks again. In particular, now I'm gonna highlight the partners after this slide, the executive strategic partners. So Edge Impulse, the leading development platform for Edge ML. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentience, making Edge AI a reality. And now it's a turn for the Platinum strategic partners. Renesas is enabling the next generation of AI-powered solutions that will revolutionize every industry sector. Sony, in terms of gold strategic partners, we have Analog Devices, where what if becomes what is. Arduino, easily deploy your tinyML solutions with the Arduino Pro. ARM, powering tinyML innovation. And here is just a reminder for attending the virtual talks on ARM for AI. Inetera, neuromorphic intelligence for the sensor edge. Microsoft, SensiML, analytics toolkit set. ST Microtronics provides extensive solutions to make tiny machine learning easy. Synaptics, engineering exceptional experiences. And now it's the time for the silver strategic partners. So Zip, Compass Marketing, Green Waste Technologies, Gravity Inc., IBM, ImageMob, Not AI, NXP, OctoML, Polling Technology, Kixel, Schneider Electric, Silicon Labs, and TDK. And that's it. Here's the copyright notice. So with this slide, I'm gonna end this brilliant tinyML talk. I hope we have all learned from Edouard the how to make tiny these models with these techniques. I really enjoy your presentation. It was a pleasure moderating this. And I think we have finished for today. With this, I wish you all the best and have a nice evening or have a good day, everyone. Bye-bye.